Hello and welcome back to the video for lesson 3.2. In this lesson, we're going to learn how to define a polynomial. We're going to learn how to find its end behavior in the graph. We're also going to learn how to find the x-intercepts and the zeros by factoring, and then also how to do a full graph of a polynomial. So first of all, the definition of a polynomial. Poly means many, and so that means we have many nomials or many terms. It has to have at least one x term, okay? An, the coefficients out front cannot be 0, which means if it's 0, then we just have a constant. So under example 1, g of x equal to 6 is not a polynomial because it's just a constant, okay? And the integers have to, or the exponents have to be integers. They have to be non-negative integers. So that's important too. The term with the highest exponent is called our leading term. And then the coefficient on that leading term is the leading coefficient. We would call this a constant polynomial. So it's a polynomial, but it's called a constant polynomial. Sometimes they're not called polynomials, but it's just a constant because there's no x term. Now on B, it says, which of the following are polynomial functions? For the ones that are, find the degree and the coefficient. So this is a 0 degree because it's just a constant polynomial. This one, we're going to multiply this out. It'll be x squared plus x minus 1. So it ends up becoming x squared minus 1. So it's a second degree polynomial because the highest term is 2. And the coefficient on that x squared term is a 1. So the leading coefficient is a 1. And it's the second degree. And then this one, this square root of x is the same as x to the 1/2 plus 3. And 1/2 is not an integer, so this is not a polynomial. So polynomials of the x to the n and their transformations. So a basic x to the n has different behaviors, is what we call them. Okay. So when your leading term has an odd coefficient, then it's going to be shaped like this or shaped like this. Okay. They're going to be opposite of each other. When it's an even, so this one is odd, this one is even. When it's an even function, then they're either going to be both shaped the same way or both shaped, they're going to be both shaped the same way. So either both up or both down. That's going to tell you that. And that's our end behavior. There's some other properties. When it's an odd, you can see that on the end behavior. I just drew that. And when it's even, so this is the odd and this is the even that I just drew up here. So on example 2, it says, find the following, tell what transformations are occurring to the base graph of x to the n. So because subtracting 1 is on the inside, we're shifted to the right 1. And our end behavior are going to be both face up. And also I want to show you, we'll do that again later on. This one is a 3, so it's odd. So it's going to be turned They will not be the same direction when it's on the left and the right. And this one is flipped over the x-axis and then also up 1. So it's up 1 and then reflected or flipped over the x-axis. Let's actually go to Desmos and look at that one in Desmos. That would be good. So let's type in y equals a negative x to the third plus 1. So if I change it from the negative, it's going to go from the right to the left because of the third. And then when I make it negative, it goes from the left to the right, it goes down. Flip the page here. So next is the leading term test for the end behavior. It says, given a polynomial function of the form that we've shown you before, the end behavior of f is determined by the leading term. So the entire leading term, the coefficient and the exponent. So when a is greater than 0 and n is odd, okay, then we have this. Okay, when a is less than 0 and n is odd, then we have this. Okay, so here we have a is equal to a negative 3, which is less than 0, and n is equal to 3, which is odd. So it's going to look like this. Now, the other situation is when a is greater than 0 and n is odd. Sorry, n is even. We haven't looked at that one. When a is greater than 0 and n is even, then they're both going to be face up. And when a is less than 0 and n is even, then they're both going to be face down. And so that's this one here. A is equal to 2 and n is equal to 2, which is even. And a is positive, so they're both going to be face up. Okay, so finding the zeros and x-intercepts for a polynomial. We're going to learn some other ways in the next lesson, but in this lesson, we're going to work on factoring. So if we want to find the real zeros, we want to factor this. So we can factor out I'm going to factor out a negative 3x. And then we'll have an x squared minus 4 left. So then I can set negative 3x equal to 0. So that means x equals 0 when I divide by negative 3. And then I can actually factor this into the x minus 2x plus 2. And then I can set x minus 2 equal to 0. So x equals 2. And I can set x plus 2 equal to 0, which is x equal to negative 2. So it had 3 roots. And we can see that. You can see all of these by graphing them. I'm going to turn off that. So if I type in this y equals a negative 3x to the third plus 12x. You can see, you can click on those. So there's one at negative 2, there's one at 0, and then there's one at 2. And I'm going to zoom out, and you can see it's just like the picture. A is negative, and our n is odd, and so it starts coming from the top left, and then it ends facing down. I don't know what I did there. Okay. And then we're also going to be talking about multiplicity, but we'll add that in a little bit. So B says hand sketching the graph of a polynomial. So first is to determine the end behavior of the function so that you know the general picture. You also want to find the y-intercept and plot it. And the y-intercept on this one, these are the x-intercepts. The y-intercept is the function evaluated at 0. So that would be a -3, 0 cubed plus 12 times 0. So both of those are going to get multiplied by 0. So my x-intercept is at 0, 0. And we could see that because it's one of our points, 0, 0. So you're going to find the end behavior, the y-intercept, and then you're going to find and plot the x-intercepts. And then you're going to find the sign and value of the function for a test value, just to make sure where these are plotted. And then use the plotted points in the end behavior to sketch a smooth graph. So let's do that for this one in example 5. So in example 5, a is equal to -3, which is less than 0, and n is equal to 3, and it's odd. So we know that it's going to be something like this in general, okay? In the y-intercept, because these are both x terms, there's no constant term, the y-intercept is just going to be at 0, 0. And the x-intercepts, we can factor. So I'm going to factor out a -3x. So I have x squared minus 9 left. And I like to factor out, if it's negative on the a, I like to factor out a negative because then I have my, what's left over, this like x squared will be positive. So I've got this term, and then I've also got this factors into an x minus 3, x plus 3. So we set this one equal to 0. So x equals 0. So I have one x-intercept at 0, 0. And then this one, I have 1 equal to 3. So I have 1 at 3, 0. And then this one, x plus 3 equals 0. I have 1 at a -3 and 0. So I can get that out here. I know my y-intercept is at 0, 0, which is also one of my x-intercepts. And I'm going to just kind of skip ahead to multiplicities. It's our next topic anyway. And show you the multiplicities. The multiplicities are how many times each factor occurs. So this x equals 0 only occurs once. Its exponent is 1. X minus 3 only happens once. It's only a factor once, and x plus 3 is only a factor once. So that means that each of these x-intercepts are going to cut through the x-axis. So at 1, 2, 3, and then 1, 2, 3, here's the -3. And we already know it's going to come from starting up. So it's going to start up. It's going to come down and do something, right? We don't know how far down, but then it's going to turn and go through this point again. And it's going to do something up, and then it's going to turn and go this point, and it's going to end facing down. And we know that from our A is a -3 and N is odd. We're going to get lots of practice. So that's where I talked about the multiplicities on the next page. If the multiplicity of a real 0 is odd, the graph of the function crosses at the x-axis. So this would be an odd multiplicity. See how it came down and just touched at the x-axis? That's because that factor occurred an even number of times. So let's look at example 6 to think about that. It says, determine the multiplicities of the real zeros of the following functions. Does the graph cross the x-axis or just touch it at the x-intercept? So we have x squared equals 0. And so that means that x equals 0. And it's even, it happens twice. So the multiplicity is 2 because that 0 happens twice. Then this x minus 5 equals 0 is an x-intercept at 5, 0, and its multiplicity is also 2. So both of these touch. Okay. B, we have this, and this are both factors. So x cubed is odd. Its multiplicity is 3. X equal to 0 is 3. It's an odd, it touches. I mean, it crosses because it's odd, sorry, crosses. And then x plus 2 equal to 0 is x equal to negative 2. That one is, the multiplicity is 1, so it crosses. And x minus 3 equal to 0 is x equal to 3. And that multiplicity is 1, and it crosses. And you can put these into Desmos to see that. Then letter C, we have x squared minus 2x plus 1. We have to factor that or use the quadratic function to find the zeros. I'm going to try to factor here. So I have x minus 1 and x minus 1. So x minus 1 gives me an x-intercept at 1 or 1 comma 0. And it happens twice. The multiplicity is 2. So it touches because the multiplicity is even. So back in chapter 2, we learned about symmetry. So we said if we put an x value in to the function and if we put the negative of x in, if those equal, then it's an even. If we put in x in and that equals the opposite of the opposite of f of x equals the same, then it's odd, or it can be neither. So let's look at example 7. And I misspoke. This is the odd is f of a negative x equals the negative of f of a positive x. So let's look at example 7. So I'm going to say let x equal 2. So f of 2 would be the opposite of 2 to the 4th plus 1 equals the opposite of 16 plus 1 is a negative 15. And then let's put in a negative 2. So f of a negative 2 is the opposite of a negative 2 to the 4th plus 1 is a negative of 16 plus 1 is a negative 15. So it's an even function. Now, let's look at the g. Let's let x equal 1. That's just easier. So g of 1 is 1 cubed plus 8 times 1 is 1 plus 8 is 9. And let's put in a g of a negative 1. So that would be a negative 1 cubed plus 8 times a negative 1. So that's a negative 1 minus 8 is a minus 9. So it's not even. And f of a negative g, right, is equal to 9. Is that equal to the opposite of a positive x? Yes. And so it's odd. A couple other things that we're going to look at when we get the polynomials are the maxima and minima, the local maximum and minimum. And you can find these where they're turning. So a local maximum point is where it's turning from increasing to decreasing. Which is increasing to decreasing. So you're going to have a high point. And then a local minimum is when you're going from decreasing to increasing, you're going to have a low point. So let's look at this graph of x to the fifth minus x cubed in Desmos and check it out. Oops. Y equals x to the fifth minus x to the third. I'm going to zoom in a little bit here, because there are some things happening here. And this looks like there might be some other crosses, but there isn't. Because if you factor out x cubed, you've got only 3. You've got 1 here at -1. And then you've got a +1. And then you've got 0. So it looks like you have a local maximum here at a -0.775. And y is 0.186. And then you have the 0 where it kind of gets flat, and then it goes down. You have a local minimum at positive 0.775 and a negative 0.186. So where it's kind of goes up and maxes out, and then where it goes down and bottoms out. The last topic of this lesson about polynomials is if you were given factors and their degree and multiplicity, could you create a function and work backwards like we did at the end of 3.1? And so it says, find the polynomial of degree 3. So the highest degree has to be 3. And we have zeros at 1, 2, and -1, and each have a multiplicity of 1. So we have x equal to 1, x equal to 2, and x equal to a -1. So if we subtract 1, we get x minus 1 equals 0, x minus 2 equals 0, and x plus 1 equals 0. And that means f of x equals x minus 1 times x minus 2 times x plus 1. And you could multiply these all out if you wanted to. X minus 1 times x plus 1 multiplies to x squared minus 1. So we'd have x squared minus 1 times x minus 2. So we'd have x cubed minus 2x squared minus x plus 2 would be our final polynomial. So there's a lot of new topics in this lesson. Go ahead and reach out if you have any questions at all.